All right. So, welcome to System Dynamics. I'm changing the name of this course next year, but I'm teaching it the same. It's going to be called System Dynamics and Control. And it was in the course description already. At the end of the course, the last third of the course roughly, we'll actually cover control systems in addition to system dynamics. Not all of control systems, just like a little baby amount, but it'll be fun. This is where a lot of the work that we did last semester starts to really pay off for us. In mechatronics, we learned how to do modeling in state space form, which admittedly is not common for you to learn how to do in an electronics course, or I don't know, mechatronics course is something that we're making up as we go, so maybe there's no usual way of doing it. But in any case, you guys learned it, and now we're going to learn how powerful that representation is, and how powerful the ideas of linear graphs and just taking a linear graph model and turning it into a state space model, how powerful those ideas are. Because we're going to get to apply those ideas outside of electromechanical systems, and we're going to also include fluid and thermal systems as well. And it'll just be a breeze. It'll be just like when we're doing a linear graph for an electronic system or for a mechanical system. We'll just draw a linear graph for a thermal system or a fluid system, and it'll work just fine, just like before, and all of the steps will be just the same. So it's really cool. We get to sort of unify a lot of lumped parameter modeling into one framework. So it's pretty exciting. Now, I thought it would be good to start with this relations among system representations handout that I gave. It was a resource on the resources page of mechatronics class. Start from the beginning with this semester so that we kind of remember the different ways we learned to represent systems and where we're going in this class. So we've actually mostly filled out this map. But we start with a schematic. So we only did electronic and mechanical and electromechanical systems in last semester. But we're going to add on to that, like I said, fluid and thermal systems. And then we can draw a linear graph. We can also draw a block diagram from it. We mostly have reserved that for the representation of systems interacting with each other instead of internal to the system, but you can do block diagrams for internal representations as well. And we learned how to go from a linear graph to a state space formulation. So all the green is stuff that we learned in mechatronics. And that state space representation, we learned how to simulate it pretty easily in MATLAB. We're going to do a lot more of that this semester. We learned how to transform that into a system transfer operator. And then we learned how to transform that into a into an input-output differential equation, right? And we learned we could even solve the input-output differential equation if we wanted to. However, what we're going to learn right now at the beginning of this class is how to deal with the state space model directly. That's the first thing we're going to learn about. How we're going to deal with the state space model directly and solve it. So previously, we never learned how to solve this. We learned how to simulate it in MATLAB, so we knew that MATLAB could solve it, but we never learned actually how to do that. So we're going to learn how to do that ourselves analytically and then numerically in MATLAB, we already kind of learned, but we'll be able to do that as well. So we'll want to verify our solutions in MATLAB, for instance. That would be a nice check on our work, our homework and stuff. So I guess I want to, sort of introduce the class through this map, because we're going to fill out the rest of it in this class. We're going to learn how to create a system transfer function from the state space model, which we're going to find is very similar to the system transfer operator. So not a lot of surprises that are going to happen there. And then we're also going to learn about the frequency response function. Now, it's one thing to transform into a system representation. Remember, these are just all system representations. It's another thing to use that system representation to do something. And so things you might want to do in any given system representation: solve it, right? You might want to solve for what the output's going to be given some input. That's a very common thing to do. We learned how to solve input-output differential equations. You guys already knew how to do that before you got into the mechatronics class, because differential equations was a prereq. But then we learned how to do that a little bit more, and we learned some tricks later on in mechatronics on how to do that a little easier using, there's this one principle that was really useful at the end of the semester. What was it called? I mean, I know. I'm just waiting for you guys.
It's like that. It's on the test.
It's something that's like. Superposition. Thank you. So superposition is a really useful way to solve input-output differential equations. Now we're going to learn how to solve the state space equations directly, which is pretty cool. Then we're going to start to turn. So we're going to take this turn. We're going to learn how to do fluid and thermal system modeling. Okay, so we're going to take a week to do that. Like I said, it's pretty straightforward to go from where you guys have been to that. It won't be too difficult. And then we're going to spend not a lot of time, 4 weeks though, on what to do when you have a system transfer function or a frequency response function. So these, that's like really, there we go. We have these representations that we can do a lot of stuff with, a lot of system analysis with. You can solve for the output of the system using a transfer function representation. You use Laplace transforms and inverse Laplace transform to do that. And the frequency response function representation, you use Fourier transforms and inverse Fourier transforms to do that. But the real power of those is not so much the solution techniques to the systems. It's the analysis in other ways. There are ways we can understand these systems and how they'll behave in what we call the frequency domain, which is described mostly by these two objects. Okay, so we'll talk a lot about that in the middle of the term. And then we're going to get to control systems, which is pretty much, okay, great, we have these system models, we can change the form of the system models, we can do some analysis of how the system behaves using the transfer function, using the frequency response function. But how do we make it do what we want? Okay. Well, all we know how to do at this point is solve for what it will do given certain conditions, initial conditions and inputs. But how do we make it do what we want it to do? And that's what control systems is all about. Okay. Most basic control system you have in your house is actually not your thermostat. It's your toilet. Okay. Toilet. Bowl, or not the bowl, the tank wants to have a certain fluid level in it. And what is in there? You guys, how many of you know how the toilet works? Okay, half, that's good. I'm not sure if I knew when I was your age. At some point I learned. Yeah. So in there's a float, and that float, when you have water coming into the tank, rises up, and if it's connected to a mechanism that stops the valve that's spraying water into the tank when it gets to a certain height, you've got yourself a control system right there. So, and if it doesn't stop it when it gets to that height, you've got problems. Okay. So it's pretty cool. But then the thermostat as well. It tries to keep your house at a certain temperature. Lots of different things like that. We will learn very basic control systems theory, and we're actually going to do. Oh, okay, I'm excited. I have to tell you, we're going to do a project in this class. Okay. Yes. Okay. So self-service has been down, which is really crappy. This class. So yeah, syllabus, all the same stuff that you guys know and love about my syllabi is here. Textbooks, Rowell and Wormley, Nice. Okay, Nice is the controls textbook. So get that by like mid-semester, hopefully. Get a used copy. It's fine if you have an old edition. The 6th edition is just fine. I'm still going to assign homework out of the 7th, so just know somebody with the 7th edition. Okay. Notes are here. You guys all know about that. Print them off before you come to class, hopefully, so you can fill them in. We are going to start here in homogeneous state response today because we're that good. There's no assignment due this week, but by golly, there's one due every week thereafter. So it's going to be great. Notice that we're starting off in chapter 10 of the Rowell and Wormley text, and then we'll do transfer functions, fluid, and thermal elements. And then we're getting into the transfer function and frequency response function thing in here. And then about week 10, we're going to start doing controls for the rest, okay? And we're going to actually build a real control system, okay, at the end of this class. So this is going to be a project. What? Oh, yeah, the toilet. My toilet is broken, and you guys need to come build it. Class resources are there. Project, okay? It's going to be a design project. It's going to be the best project. Everybody's saying it. It's going to be huge. Huge. And also, related to this is kefir does the body good. Has anybody ever had that before? Kefir? The milk stuff? Oh yeah, it's pretty gross, right? But I like it. So I culture my own of that. Yeah, it's pretty cool. It's kind of like yogurt.
Okay.
So here's the thing. It sits on your counter and it ferments. You put these little cultures in it, and it sits on your counter and it ferments, and then you strain out the little, they call them kefir grains or kefir grains, and then you put them in the next batch of milk, and then it does it again. It's pretty cool. It's very tangy, very tangy. So it sits on your counter and it ferments, but it's the two things that are the two big factors is how many kefir grains you have in it and what the temperature is, okay? So we're going to build something that's going to control the temperature of that for me. Yeah, okay? And it's going to be a real hardware thing, and we're at least going to get to the point where we could fabricate it. I want to actually have you guys fabricate it. Because you guys are juniors, and you guys don't get enough hands-on stuff to do as juniors. Senior year, you get a lot of it. But junior year, you don't get enough. So I want to give you guys like something to actually build. So we'll see. It might be fun. I think it's going to be fun. I will enjoy it. I don't know if you guys will, but it'll be cool. And so it's pretty simple. It's just a temperature controller, but we'll use probably, we have some Arduinos lying around for a microcontroller, and yeah, we'll just do that. So it'll be pretty fun, and we'll learn how to do all that stuff. So later on in the semester, we'll learn more about it. It's going to be pretty cool. If you're not on the Slack, get on the Slack. Okay. Homework every week, not graded, but there's a quiz. I will say I was disappointed towards the end of last semester at how well people did on the quizzes and how poorly they seemed to understand the material from the homework. I don't know what was happening there. I like to think the best of effort.
Like hours upon hours to figure out. For me, it was like 4 hours of problem.
Yeah, no, people. So I think that actually, here's the thing that is weird: is the people who struggled on the quizzes seem to do better on the tests, and the people who got really good grades on the quizzes struggled on the tests. And that makes me feel really suspicious. I don't want to be suspicious, but I feel suspicious for that reason. So if you found yourself taking the easy route last semester, I encourage you to not do that this semester, I guess. I mean, I'm sure that everyone here was not taking the easy route, but I'm just saying, in case you know somebody who did, in another class or whatever. So, we'll see. And if I continue to see issues with that, I might start having you guys turn it in, because the point is for you to do the homework and understand it, not to get a good grade on the quiz. That's not the point. Okay, exam policies, don't cheat. Okay, grading policies, homework quizzes are worth 15%. Notice not a whole lot of your grade, so cheating on them is not good. Obviously, if you were cheating, but you're not. Project, 15%. So I put a lot of weight on that. It is very important. It's really good. Probiotic. Midterm exam is only one in this class. So we're only going to do one midterm and a final. So 30 and 40%. Notice how highly weighted the class is towards taking those exams. It's actually less highly weighted than last semester, because on this semester I have a project in there. So now it's 35. This was 35, I think. I'm pretty sure. Oh yeah, there were 3 exams. Yeah, that's true. That is true. So anyways, you guys are going to do great on those. May even have a take-home midterm. We'll see. Play your cards right.
No.
Okay.
No.
You guys never had one from me, did you?
We've heard the stories.
Yeah. They're so fun, though. Okay, yeah. Don't cheat. I take it seriously. Correlation of course and program outcomes. This is all for ABET stuff. Look at these tables. So fun. All right.
No one understands that.
I know, nobody understands that little graphic way.
This? Yeah. So
I mean, I get it.
desired course outcomes are numbered, and then desired program outcomes, so like mechanical engineering program outcomes are like, you guys should be able to design a system, component, or process to meet desired needs, okay? Which sounds really fun. And then we say, okay, here's this course. This is what we want. Like, you'd be able to solve equations of state analytically and numerically. So here we go. Whatever number that was. Let's see. 3.
It was 3.
And I talked about C. So 3, look at that. It helps you. It helps you design systems.
It's just a
So what about 3G?
G, no.
What is G?
G is an ability to communicate effectively. So everything applies to everything. So we just say, like, how much does it apply? Like, where's the cutoff?
It's because we don't have any. I feel like H is kind of important.
It's just for accreditation purposes.
Exactly.
I don't know if that really worked covering the microphone, but anyways. All right. So, I mean, I believe in those. It's kind of like that. So, you might notice that my website got a little bit of a sexy redesign towards the end of last semester.
Someone is their third year review.
Somebody did. I don't know if they're done yet, but the committee was done, and they were like, thumbs up. So that's good. So I'm still here. Yeah. So at least, I don't know, at least they thought I should be here. We'll see. Okay, so this is all of the fun stuff that we're going to do this semester. But, as you know, I'm always focused on the material and not so focused on the administrative aspects, like taking attendance. You guys are here, right?
Yeah, we're here.
Raise
Okay.
your hand if you're not.
Okay. If you're not here, tell me, yeah. So I am going to probably on Wednesday take attendance, but we need to make some progress. I really hate all the, like the syllabus stuff. We totally covered it, but yeah. So this class, though, this is where it's at. This is the map for the class, and we're gonna try to keep coming back to this and remind ourselves where we are, what we're doing in this class. Okay. Whew. Now we get to the good stuff. So, the first thing to note is that this section and the material in it are totally misnamed, but they're called this in the textbook, so I just don't like the name. They call it homogeneous state response. But really, we should call it something like initial conditions state response or unforced state response. Because, as you're going to see, we're going to actually plug in the initial conditions. And if we plug in the initial conditions, that would make it the initial condition response. So, anyways, just bear with the poor choice of nomenclature. So recall that we can write the state and output equations for a linear time invariant system in this form. And we learned how to do that. We learned how to draw linear graphs of some schematic model that we have, and then we wrote the continuity, compatibility, and elemental equations, and we put them into state space form. And that's what this is, state space form. So this is our sort of our touchstone. Every system that we're considering in this class can be written this way. Okay? When I say LTI, I mean linear time invariant. So the linear part means that you can write it in this matrix algebra form where you have a matrix multiplying the state variables, x, so that x is the state vector, right? And A is the matrix that multiplies it. That just essentially tells us how those state variables enter into the dynamical equations, right? And U is our vector of inputs, right? And the inputs could be like a voltage source or a force, something like that. They're listed in the input vector. And then B is the matrix that describes how those inputs enter into the dynamical equations. Okay? And then Y, the second equation, y equals cx plus du, just describes how those state variables and input variables, so x and u, how they affect what we have chosen to be our output variables, okay? And the output variables are just variables that we care about. They might just be the state variables. Oftentimes they are a state variable or maybe 2 or 3 state variables. Other times it's some combination of state variables and inputs. And so we may or may not need to use C and D to describe how those state variables and input variables contribute to the output equation. So we can solve these equations both analytically, which chapter 10 describes, or numerically, which chapter 11 describes. I'm kind of skipping chapter 11 in the textbook. It's how to solve the state equations numerically. Now, I think it's a great topic, and I wish we had time to cover it, but it's really more of a topic for a numerical analysis course, which is an elective you could take. So we're not going to cover that in detail. We actually know how to use MATLAB to simulate these things numerically. We just don't know how those solvers actually do it, right? So we're just going to use the black box of LSIM and, well, mostly LSIM. That's mostly the one we're going to use. You can use STEP. It gives you the step response. You can use, I think there's an impulse response one. Yeah. So, yeah, LSIM is probably the most versatile. We'll use that a lot. ODE 45. Did you guys learn that in your 305 class, Engineering Computer Applications? Yeah, so ODE 45. That's actually, so LSIM is just this wrapper around those ODE solvers, like ODE 45 and et cetera, and they just crank through. It's almost as easy to use ODE 45 or 15S or depending on your application. But LSIM just chooses for you. It's kind of nice. Okay, so what we're going to learn about first is how to solve them analytically. And it's actually not too bad. So recall that when solving for scalar first-order homogeneous solutions, we found them to be of this form. So we didn't always write it this way, but you can always rewrite a first-order homogeneous differential equation as the time derivative of one variable, you could say plus or minus a constant times that variable equals 0. That's the homogeneous equation. And we solve that equation. We've done this a lot. This is the simplest differential equation you can solve. And, well, I don't want to say that as a blanket. It's one of the easiest. Whenever you say something absolutely, people come up with a better example. But so this is the homogeneous solution. Well, the homogeneous solution technically has just a constant here. But if we plug in the initial condition as x of 0, we find out that x of 0 shows up there as the constant. So it's a pretty nice little solution. Now, we're going to use this to cheat a little bit, okay? So, okay, where a is just a constant, a real number, is a system parameter, and this is the initial condition. So the exponential term here, e to the at, has this power series representation. Okay? So in one of your calculus classes, you guys learned about power series expansions of 3, Calc 3. Yeah, so your power series expansion of e to the at, this is actually the definition of the exponential, is this. Whew. With, you know, a bunch of terms. So, an infinite number. So this is the power series representation of e to the at. Now, here's what we're going to do, sort of tricky. Consider the homogeneous vector state equation x dot equals ax. So we said all of the inputs equal to 0, so u equals 0, right? So I go up here, and I said u is 0, there's no inputs. We have a homogeneous situation. Okay, that's what homogeneous system is one with no inputs. So we have x dot equals ax. So we'll go back down here. X dot equals ax. We want to solve this. So we want to say, for the state equation, simplest case, homogeneous case, no inputs, how do we solve it? That's what we're going to go for first. So let's sneakily guess that it has this solution, okay? The homogeneous solution is something very analogous to what we have here. Because look, this looks a lot like x dot equals ax, looks a lot like this x dot equals ax, right? They're very similar. This is the scalar one, this is the vector one. So let's say maybe, so one way to solve the differential equation is to guess what the solution is and then check and see if it's right. So let's just be sneaky and guess. Maybe it has the solution, instead of a 1, let's try an identity matrix, which is sort of like a 1. A, the scalar, let's try the A matrix there, times T. And then wherever you see the A scalar, we're just going to stick in A matrix, okay? And otherwise it has the same form. Let's say that all of that is our, I guess, the factor out in front of the initial condition in our solution. So up here, can't quite get it on the same screen. Up here we had x homogeneous being e to the at times x of 0, right? So we're saying maybe in this matrix case, if we say this is sort of like e to the at, but like for vectors, times the initial condition. Maybe this is a solution. We don't know. But like I know, and I'm going to tell you, it works. We're going to check it in a second. We're going to define this to be e to the at, the matrix exponential, which we also call phi, the state transition matrix, which I put in big boxes on the next page. Okay. So let's check this guess. The time derivative of this is the following. So when you take a derivative of a matrix or a vector, how do you do that?
Linear operator you apply to each term.
Yeah, so it applies term-wise or element-wise. So you take the derivative of each element of the matrix or the derivative of each element of the vector. So it's what you would hope it would be. That's what it is. So if we take the time derivative of the identity matrix, the identity matrix has some 1s in it, and it has some 0s in it. What are the time derivatives of those 1s and 0s? 0. So it gives you the 0 matrix back. And the time derivative, so the A matrix here, time derivative of this term, the A matrix is the matrix of constants, right? With respect to time, because we said it's time invariant. You can have a time varying system where your parameters depend on time. We're not going to consider those. So all of these are constants multiplied by t. And we take the time derivative of a constant multiplied by t, you just get the constant, right? So we just get A. And then what happens to this squared term? This is all a constant, but the t squared, so you take the 2 down, and you have t, and there's 2, but the 2 cancels with that highest term in the factorial. And so essentially you just get this series that emerges. It's pretty much straightforward, I guess. Each term you take the time derivative. It drops the t polynomial by 1, and your denominators all have the top factorial term canceled. So it's pretty straightforward. And then multiply by x of 0. So let's take a look back here. So in this new series, the 0 term goes away. You can factor out the A matrix here, because the A matrix shows up in every single term, right? Shows up in every term. So we can factor it out on the left. So when we do that, notice what happens. This first term that we factored the A from becomes identity matrix, right? The second term becomes AT. So there's AT. Third term, et cetera, and you get kind of what you started with, right? This is the homogeneous solution that we assumed up here, right? And so we can just write X homogeneous there, and we have now shown left-hand side is still X dot equals AX, and we've shown that we got the homogeneous state equation out of assuming this solution. So that was our method of demonstrating that this is in fact a solution to the equation. Yes?
So the second equation is the integration.
This one here?
Yeah.
This is actually, so all I'm doing here is factoring out A. So in this term here, notice that every term, so this 0 goes away. Every term other than the 0 has an A in it, right? Left multiplying. So we can factor out that A from every term. Okay? When you factor out that A from every term, what's left, this term right here is just exactly the same as this term right here, right? And so if you combine it with the initial condition right here, it's the homogeneous solution, X, that we assumed at the beginning. Okay? It's a little bit, maybe a little bit tricky to follow. I mean, this is a derivation. Hopefully you guys become more and more comfortable with them over time. I know that they're not everyone's favorite. So we checked it. Turns out this is a solution. It actually works the same. I mean, you can do this demonstration with the scalar case too. It works almost identically. So that's awesome. So you probably saw a derivation kind of like this in your differential equations class for the homogeneous solution of the first order system. That would be my guess. I don't know. Everybody teaches differently. Okay. So this magical matrix series that we wrote out here, we call the matrix exponential. Okay? And we denote it e to the matrix AT. Okay? This doesn't mean that you have a scalar term in each matrix that's e to the whatever that term is. That only works in a special case. So in general, this is defined as being this series, okay? Just like the scalar exponential is defined as being this series, or it can be defined as being this series. So it's a very similar series. And the series actually, there's a name for it. It's called the Piano Baker series. Kind of a famous series. And the state transition matrix, phi, is defined as being the matrix exponential. Okay? So we have sort of two names for the same object. We can call it the matrix exponential of the A matrix, or we could call it the state transition matrix. State transition matrix is a little bit more descriptive, and you don't have to say the matrix exponential of the A matrix. You can just say the state transition matrix for the system. Okay? Now, you don't have to go through this derivation every time. We know that this is a solution, or that this that our assumed homogeneous solution right here is the solution to the homogeneous equation, right? So it's just phi, the state transition matrix, times the initial condition. That is the solution. Okay. Now, we don't necessarily know how to compute e to the AT other than this big series, right? But we know the definition, so that's the start. So phi is usually computed from a method other than from its definition. So we will cover this method later. It's probably Friday. We're going to cover this. So don't feel like it's coming a long time from now. But we can use the definition for now to do some things with it. And we're going to do an example with it today. So here's the example. So example 10.1 in your book gives that for this A matrix here, this is the state transition matrix. So it's worth going through that example. I think it's interesting. But you have to compute it from, you have to recognize series expansions, and it's good, but I don't think it's super useful. So I don't give you guys a lot of problems like that. However, and I don't expect you to be able to recognize those on tests, for instance. But I do want to understand how to use the state transition matrix. So for some initial conditions, we'll call x of 0, the homogeneous state response then, by definition, has to, well, by the way we define the state transition matrix, this has to be the homogeneous solution, right? So here's phi, and we're just going to use the one that they found for us in the example. We're just plugging it in, times the initial condition, which we expand to be the initial condition of the first state variable and the initial condition of the second state variable, okay? Now we do the matrix multiplication, which is, we'll go through the steps because maybe we're a little rusty. E to the minus 2t times x1 of 0 plus 0 times x2 of 0. So we are left with e to the negative 2t x1 of 0. And this is going to be a 2 by 1, right? We have a 2 by 2 multiplying a 2 by 1. The inner dimensions collapse, and we get a 2 by 1 vector out. Better be a vector, because this is a vector on the left-hand side. So this lower term here is found by multiplying this e to the negative t minus e to the negative 2t times x1 of 0 plus e to the negative t times x2 of 0 here. And that is our second term. Now, this example requires that the power series are recognized as describing exponential functions. And I think that's a difficult task to do. It's not like impossible, but I think it would be kind of challenging. And it's not, I don't think it's super useful to do. Because we don't usually compute the state transition matrix this way. Like I said, we're going to learn a better way to compute it soon. Friday or next week. We'll see.
Sorry, you're talking about how to get the e to the negative 2t, even if 2t minus e to the negative 2t. Like, how'd you get that?
Yeah, this part?
That's what you're talking about?
Yeah. So getting this, you can do it analytically from the definition in some cases, but I think it's a little hard to see. I don't recommend that method. I recommend this other method that we're going to learn next week. So we're just going to use one that I'm just giving to you in this problem just to use it. And then we'll learn a better way to find it. We can always go back to the definition, which is what the example does. And you can look in the example problem 10.1. It explains how to go from this definition to this phi. But it's not, I don't find it to be super useful because it's not the way we usually compute it. But probably a good exercise. Now, let's go over to MATLAB and compute the first few terms of the matrix exponential and see if we can get it to converge to the analytic result. So notice, this is our solution. Our homogeneous solution is here. And we did it. It was super easy once we had phi. It was just a matrix multiplication, right? So all we need to do is find phi, and we're good. But we know phi from the definition, and what I'm going to do in MATLAB is compute the first n terms of this and see if it converges close enough to it to get a good solution. So that's what I do in MATLAB, and I'll quickly show you this now, and we'll go through it in a little bit more detail on Wednesday. So what I did was I said, okay, let's do the first capital N terms in the Piano-Baker series as an approximation for the state transition matrix, okay? And we're going to compare that to the analytic solution that the textbook got in the example problem. I'm going to say, okay, if we just approximate it with like the first 25 terms, how does it do? Is it close? Like, how many terms do we need? So that's what we're going to talk about, how I constructed this on Wednesday. Okay? All right, yo, guys. I'll see you Wednesday. If you have any questions, let me know. There's homework due next Wednesday and a quiz. Not this Wednesday. Don't worry. I thought about it for a minute, and then I was like, no. I'm not planning on a mechatronics review.
For a stroll.